Hello and welcome back to another lecture from organic chemistry. In a couple of lectures before, I showed you how to protect a carbonyl group while you want to run the reaction in another side of the molecule. And for that purpose, we use diol to protect any carbonyl group. And at the end, we release the diol and we managed to recover the carbonyl group. Now, can I take a carbonyl and get rid of it completely and replace it by a saturated group? The answer is yes. And you can use actual Wolff-Kishner reduction method to take a ketone and transfer it to alkane. And does it work with aldehyde instead of carbonyl? The answer, instead of ketone, the answer is yes. It can be used for both aldehyde and ketones. The first step of this reaction is like in the presence of trace of acid, we can add NH2. NH2 to group 2, technically carbonyl, and it will give us a double bond between nitrogen and carbon. Now, the compound that we use for this purpose, we call it hydrazine. This is the compound, is technically two nitrogen, then nitrogen atoms that each one is carrying two hydrogen attached to it. And so in the presence of trace of acid and hydrazine, we can take the carbonyl and transfer it to C and double bond, while nitrogen is still attached to NH2. Now, we do have acidic H attached to nitrogen, so if there is a base there, that base very soon is going to go after those H's and it will take them out of the system. And so in the presence of strong acid and strong base and also a bit heat, we can get rid of the hydrogen atoms, and at the end, that's going to give us a chance to to make nitrogen good living group, and then nitrogen, those two nitrogen, they will leave the system as N2 while we are replacing CO by CH2. So the thing that is happening at the end is CO got replaced by CH2. Let's go after it. The first step of the mechanism is like we have addition of hydrogen to the carbonyl, and after we getting this compound, now we can add a strong base to it. The strong base is going to go after the acidic hydrogen. We can find them there, and it will remove one acidic H, and that means we're going to get a lone pair. Now, what will happen with that lone pair? Lone pair, it can be shared with the neighbor nitrogen in order to make a double bond, but that's going to leave us with a negative charge on carbon. And so, as you see, we took the lone pair, we shared it with this nitrogen, and then the double bond, we gave it to double bond. We shared this one, and we gave the double bond to carbon. Now we got the negative charge there. Negative charge on carbon is not stable. It will be saturated or neutralized very soon by acidic H from solvent, and our solvent is water. So now we're going to take an acidic H from water, and that's going to leave us with H attached to carbon. And now on the carbon also we have N2. Okay, N2, that's the terminal nitrogen does have another H attached to it. Now, can I take that H? Answer, until you have a basic, basic substitution, basic group inside the solution, and yes, you can take that acidic H. And if you have enough from hydroxide very soon is going to go after H because it's a strong base, and it will remove that H. That's going to leave you with a negative charge on the terminal nitrogen. Look to the terminal nitrogen. Already has two lone pair. Right now it has two lone pair, and it can use one of those lone pairs. Share it with the nitrogen, and if that one happened, the nitrogen I'm going to highlight, that nitrogen, the internal one, and it will technically get a positive charge if we accept a lone pair from nitrogen and from the terminal nitrogen. So it's going to turn actually the internal nitrogen to a good living group, and that's the reason. And we will lose entire of this group as N2. And so what will happen with the sigma bond that we have between nitrogen and carbon? That sigma bond, it will show up as a lone pair on carbon, and that lone pair on carbon again is not going to be stable. It will take another H from water, and it will leave us with two hydrogens on carbon. Okay, those two hydrogen we got them from water. Okay, those two hydrogen that I showed on carbon, we got them from water. Okay, or technically our acidic solvent. So the entire of the reaction I can show it as this. We had the carbonyl group, and that carbonyl group turned to such a thing. Oxygen got replaced by two hydrogens. practice some example about it. Imagine you have a benzene molecule, and this benzene molecule, you want to turn it to a benzene ring, a phenyl ring that it has like a CH2 attached to a tertiary group. Okay, so the thing that happen is hydrogen atom got replaced by this substituent. How can I replace hydrogen by such a substituent? You might say, why don't you simply go with Diels-Alder reaction, and that's gonna, go with the Fiedel-Crafts reaction, and that's gonna turn, hydrogen to any substituent that you want. Okay, so I want this substituent, and I want this one to be attached to the phenyl ring. So you might say, go with this. Go with such a thing, and this is the substituent I wanted, and add aluminum chloride to it, and that's going to give you such a compound. Carbon, it will have a positive charge plus aluminum chloride, and this one will have negative charge. Now, next step, this species, it will attack the benzene ring. So if I add the benzene here, the phenyl ring to it, I will get such a compound. Okay. The answer is going to be no. Okay, and why is not going to happen? Because the species that I'm going to highlight is not stable. This one is not stable. Then what's the reason behind it? Because you got a primary carbocation, and that one actually can do some rearrangement. So I have a primary carbocation. If I move the CH3, if I move it here, that's going to give me such a thing. Now the positive charge is sitting on a carbon that is a tertiary. Okay, so from a primary carbocation, I managed to turn it to a tertiary carbocation. If there is a possibility to do such a rearrangement, then the molecule or that species is not going to ask your permission to do it. It will do it. And that means you can't use this method to put such a substituent on any benzene molecule. And you need to use another technique. And the technique that I'm going to use, I can use still the Fiedel-Crafts reaction, but I will use Fiedel-Crafts isolation reaction. So let's go with this. We're going to use, again, this, and I have a chloride here, but the compound that I'm going to use, forgive me, I'm going to use this. Instead of Cl, I go CO, and then I will put Cl here. And my Lewis acid, it will be aluminum chloride. And that's going to give me such a compound. Double bond with a carbonyl. Now we will have a tertiary group attached to the carbonyl, plus aluminum chloride, and this one, it will be tetra, and because it's tetra, it will have a negative charge. Okay, so I got a carbonyl. Okay, I got a carbonyl that's attached to the benzene molecule, but that's not really the final product that I wanted. I need to get rid of the carbonyl group, and now I need to reduce that group, and that's going to actually give me the final product. So until now, we have this. And if we treat it with trace of acid and hydrogen, that's going to give us such a compound. We'll have a double bond between nitrogen and carbon, and this one will be NH2. Okay, and the next step, I will take that one and I will treat it with a strong base and also heat. So next step, take this compound and treat it with strong base. And the base I'm going to use, it will be sodium hydroxide or potassium hydroxide. And the solvent, it will be just H2O, and I will use heat. And you might see it, they show it by just delta sign, that means it's heat. And that's going to do the reaction, that's going to do the job for us, and it will turn entire of this one, it will turn it to technically as nitrogen gas, so it will be N2. While here we will have carbon attached to two hydrogens, and other side also it has a tertiary butyl group attached to it, and that's going to be my final product. So the final product, I got such a thing, which is the one I wanted. Okay, so I did an acylation first, and then I reduce it by hydrogen, and I treat it with a strong base in order to take the hydrogen, the acidic hydrogen, those two acidic hydrogen, I take them out of the system in order to make nitrogen a good living group, and nitrogen left the system as N2. And this is going to be the end of this lecture, and thank you very much.